This was the only thing you could write down as far as statistics and reality and whatever goes. You can always rescale epsilon. If there's a factor 2 here, then the new epsilon can absorb the 2, so this was completely unique. And the transformation for that spin 1 field, this field was this. Now, some of you asked me, what about spin? Because I gave a discussion yesterday. Well, we have two kinds of particles in nature, bosons, as we call them, and I discussed the story of Bose, and fermions. Now, there's a very deep theorem called spin statistic theorem, and I did not explain that, but let me quote it. It says that bosons should always have integer spin, and fermions have always half-integer spin. Now, fermions don't like each other, so they sit a bit away. You can't put them all on the same spot. That's why we have stars, like white dwarfs and so on. They are made of neutrons. Neutrons are fermions. So electrons are also fermions. So they sit in the outer shell of the atom. They can't sit all on top of each other in the nucleus. And electrons have spin a half. So that is in agreement with the spin statistic theorem. They're fermions, a half is half integer. That scalar field phi here, if it is the real Higgs boson we are going to look for, it is a spin 0. So it is a boson, and 0 is an integer. Now this field lambda, we could call it the electron, and then we call this the Higgs boson. So in a realistic model this would be half integer, and the quarks you may have heard about have spin a half. But these gravitinos I was discussing yesterday, introducing, were also fermions, so they should have half integer spin. But when you go to 4 dimensions, it turns out they have spin 3/2, as I mentioned yesterday. That's half integer. And the bosons for the gravitational field, the metric field, has spin 2. So that's a boson again. And that means light, for example, we can make lasers, then all these photons sit on top of each other, a very narrow beam. In the future, but it will not happen in my life, I'm sure, you could make a graviton beam laser. So then a beam of very collimated gravitons all on top of each other, you could shine and just eradicate anybody who asks a difficult question. So that's, gravitons are bosons. So that was a statement about spin and statistics. But this model, I've said it many times, let me say it again. In this model I do not have spin, so it's too simple in that. The rest is good, but spin is absent. That somewhere, when simplifying the model down to the most essential, you lose some nice features. I don't think spin is essential in this context, so, yes?
This theory is not so consistent?
No. I can still declare in 1 dimension that this has spin a half and this spin 1, and then I save the spin statistic theorem. But I don't go wrong if I say it is spin 12 or so instead of a half. So in this case it is not unique. Spin has, let me explain why. It's a good question. Spin has something to do with rotations. Namely, if you rotate the thing around, then it is in a different representation of the rotation group, as a mathematician would say. But in one time dimension, I have no space, so I can't do rotations in space. So in that sense, the concept in this model doesn't make sense. If I would have 1 time coordinate and 2 space coordinates, I could just make a rotation in that 2-dimensional plane. If I have 1 time and 1 space, I cannot make rotations in the 1 space coordinate. I can only flip. I have no other dimension in which to rotate when I have 1 space dimension. So anyhow, now then we yesterday extended this to local supersymmetry, and I gave arguments why that is the same as supergravity, because somewhere along the derivation we saw the need for introducing a gravitational field. I called it H. Maybe the name was not so fortunate, H, because the metric I called G mu. So I'm going to clean up these notes and put them on the net for those of you who want to read them once again, and then I'll change H into G. It's more natural, but historically I wrote H. Now, this model, we saw halfway that there was an ambiguity, how you could proceed. And I said, I choose one way, and I gave you the answer. But the question, of course, many of you asked is, what would have happened if you went the other way? And in fact, let me tell you, all the time when you do this procedure, you find at every stage usually ambiguities. You can parameterize them by parameters x, and the next time y, and then z. So in the end you get a Lagrangian depending on x, y, z, and whatever. In all cases I've worked on, and I've worked on an enormous number of cases, you can always remove these ambiguities by redefining fields. For example, if you have model number 1, and you have somewhere else model number 2, and here you have fields lambda, and let's call the fields here lambda tilde, then you can go from this to this formulation simply by replacing lambda here by, for example, 1 plus 2h square root times lambda tilde. And if you do that, and you view this model as a model of lambda tilde, you find it is this formulation. So all these different models you get by choosing different values for these ambiguity parameters x, y, and z, they're all related by what we call field redefinitions.
And H is another field?
H was that gravitational field.
Yeah. And X is the space coordinate.
X was the space coordinate in this example.
Yeah.
Now, there's no theorem I'm aware of, and since I think I've done most of these calculations in the world, I doubt it if anybody else has a theorem, but we all see all the time that it is related in that way. Now, some of you ask me, if it is unique, how come that we have more models than only one? Well, the starting point you have always to define in this method. So, for example, I started here with this term, and then I wanted to add a fermion, and that was rather unique. But in higher dimensions, I could have, for example, started with a spin, let's say spin 1. That is a boson, spin statistic theorem, and I'm not going to say how I write it. The electromagnetic field, the Maxwell action has spin 1, so I could take that, but let me not tell you what it is. But then, of course, I could have added for supersymmetry a spin 1/2 or spin 3/2. Now, you always have to be 1/2 unit away from this one, and that has to do that the parameter itself has spin 1/2. And so then you do products of representations of the rotation group, and you do Clebsch-Gordon decomposition, and then you see it's either this or this. So if I tell you spin 1, I don't know yet the whole starting point. I have also to tell you I start with spin 1/2 or spin 3/2. But once I've given the starting point, this method I have derived as you is unique. Each time I may get these parameters x, y, z, but if I redefine fields in that way, I consider that still unique. Because physics, we can prove that doesn't depend on whether you use formulation 1 or formulation 2. That's a theorem which I'm not going to prove here, but it is a theorem. It's not a conjecture. Now, so the transformation rules, which the complete local model, which I wrote there, but I'll write it here now, what we got was the following. don't have to learn it first and then apply it. They can go along. Now, there are many fields in physics these days where people haven't found the geometry yet. I always think the Carl models, as they are called, they're very ugly. They're always known to show Carl models. They're low energy effective descriptions of what happens, but there's no real, well, there is a real underlying theorem. People like to use a lot of description. And in these models, the geometry is not known. It could very well have been also in general relativity that people knew only a few expansions, not the whole beautiful geometrical concept. So there's always a second step. These Newton methods, they give you perhaps the algebra as an action closed form. But the geometrical meaning of the result is not yet there. Einstein was lucky that he had Grossman as a roommate who taught him that. Now in supersymmetry, I'm now going to come to superspace, there is a geometrical meaning of all this algebra. You may wonder, what is the meaning of a supersymmetry transformation, geometrically? Physically, it transforms boson in a fermion and boson. And since there are only two kinds of particles, it's like the human race, there are men and women, there's not a third category. So bosons and fermions. The symmetry between the two is, of course, the ultimate. That's why it's called supersymmetry. A lot of people believe it couldn't be known, but it could be known. And it's there. And as I said, nature, whether nature knows about it, we don't know, but it's our ansatz that it perhaps does, and we work on consequence. But it doesn't tell us what the geometry of this epsilon transformation is.
Well, since the epsilon is local in time,
yeah.
Right? That sort of means the time axis doesn't have its linear structure anymore.
Yeah, local means that every point can be treated differently.
Yeah.
That's the concept of gauge theory. That you also would have an ordinary gauge series where the currents are local.
Yeah, I know, but we should typically think of time as a well-defined affine structure anyway, not just scale and up to.
Yes.
So, aren't you destroying it with the epsilon? The local time. I mean, the theory is.
I consider all possible epsilons at every point. In that sense, I haven't destroyed this homogeneity in time. I consider every epsilon and I can take an epsilon at any point in t.
Yeah.
So in that sense, I don't treat any point in t differently from another point. So in that sense, I would say I still have the idea that it's homogeneous in time. Maybe there's a point you want me to discuss afterwards. Clearly don't see your point. Now, the geometry, which I'm now going to discuss, is superspace. And that's all right. I'll try to do it here. And superspace was invented by Sullivan and Stony. So they were physicists in Trieste. But they had quite an interest in mathematics also. And they applied a very old idea in mathematics, which is called cosine methods. Oh yeah, I'll do it there. And the idea is that local supersymmetry and rigid supersymmetry, that is a symmetry which is just as the same as translations, but in a different direction. So translations on a coordinate means that you replace, in our case, t, the coordinate by t plus a. Now I'm going to explain that supersymmetry acts on a different kind of coordinate. I will denote it by theta. And it replaces theta by theta plus epsilon, where theta is now the Grassmann variable, and epsilon is our old epsilon. So if you compare these two things, you then see that it's natural to consider a space, which is called superspace, which has two coordinates, t and theta. And we can have fields, which are called superfields, which are fields phi that depend on t and theta. They could have indices, these fields, and often they do, but in my simple model they don't. Now, this theta being in Grossman variable, it follows that theta times theta is 0. And since theta and epsilon are Grossman variables, let me for completeness also say that this is 0. And also epsilon times epsilon is 0, but I will always work with first order of epsilon. So we'll never have to look at epsilon squared. So these are the properties of Grossman variables. And I'm going to explain that supersymmetry has this geometrical meaning, a translation in another direction. Now, it is of course conceptually very difficult to view a Grossman coordinate as a direction of a space. Time, you can think. If you move in time, you get older, but we know you can move in time. Moving in the direction of Grossman variable is difficult. There's no norm in Grossman space. But you can add Grossman variables. You can add one to another. So in that sense, theta going into theta plus epsilon can be defined. So now what I'm going to do is I'm going to rewrite this system in superspace here, and I'll show you that everything I did here can be rewritten in terms of superfields. And that's a formulation everybody now uses, not only abstruse theoreticians like me, but also people who work in the laboratories where they're going to be expert proof of the supersymmetric particles. They use this, everybody uses this formalism. So I'm going to explain that formalism now. So first, I must begin by the beginning. So we had a field phi and lambda. How can we put them in a superfield? Well, I want to write somewhere phi and lambda here, and maybe a theta. Now, the first observation is that any superfield can be expanded in a power series in theta. I will assume that you can do that. But there are only two terms. They can have a term independent, let me call it phi naught of t. Then there's a term linear in theta, phi 1 of t. But I can't go further, because the next term will be two thetas, phi 2 of t, and so on. But theta times theta is 0. So superfields are always a finite number of terms. In this case, only two terms. Now it seems natural that you must put that field phi there here and lambda here, or the other way around. But which is the right way? In order to explain that, I go back to the notion of dimension. We had seen, I'm going to, this is my aim. It's a projection that I'll show you works. But of course, handling this idea is an act of inspiration. This you cannot derive from first principles. This is what Salamas does either. But I'll show you it works. So epsilon, you remember, when I did counting dimensions, I dimension minus a half. You remember that law, I checked. Phi has dimension minus a half. Lambda has dimension 0. And epsilon has dimension minus a half. Do people remember that? So theta and epsilon have the same dimension. So the dimension, because I want to add it. And therefore, I know that the dimension of theta is minus a half. But I recall that phi had also dimension minus a half. And lambda had dimension 0. So there's only one way you can write this in a superfield, the phi and the lambda, as follows. Phi t of theta is little phi of t, and that is this here, plus theta lambda of t. Now the dimensions match. Minus a half here. Minus a half plus 0 is also minus a half here. Now theta, I want to be real. So theta, Hermitian, I can introduce a notion of Hermitian conjugation, and theta is real. We already required that epsilon was real. And since I add epsilon and theta, it makes sense if one is real to also require that the other is real. But lambda is also real. And this combination is not real, because if you take the Hermitian conjugation, they change places. And then if you want to bring them back in the original position, you get the minus sign. So I will put an extra factor I. Now it is real. This I is of course the same I, and you see it, the same argument that I have two Grossman variables and I want it to be. So this is my first superfluid. Now I would like to write an action S. For the action, I want to write an integral over t, but also an integral over theta. And now I have to define what do I mean by an integral over theta, because we're now in a very strange field of Grossman variables. We must introduce a notion of an integral. So, now I guess that many mathematicians know this, but let me assume you have never seen it, and maybe if I'm going too slow, you must tell me. But when you define an integral, like the back integrals or so, you have to specify some properties the integral must have. And I'm introducing now with mathematicians, so they appreciate the notion of translational invariance. So I want the notion of an integral over theta. So for the time being, I will not look at the t integral, which anyhow is an ordinary Riemann integral. So there we don't have to think. We have now another kind of integral, which it is. There's no boundaries like minus infinity, plus infinity for theta. It's just a symbol integral. But I want that this symbol associates to this expression a number. And moreover, I want that this integral is the same as this integral for any epsilon. Now, this is what we call translational invariance of the integral. In physics, there's a reason we want this. It's not because mathematicians say it is nice to have such a property. But the reason is that in physics, when we do path integrals, we complete squares. And at some point, we then want that after we complete square, the integral over the square is the same as before. And for that, you need translational invariance. So there's a physical reason for this and a mathematical reason. Now, Mathematicians was a mathematician, of course. I met him before he died. He died in a drafting experiment. But he was the one who invented this. Now, f of theta, you get the constant. Could be.
That's what global constant.
Yeah, the epsilon at this point is anything that does not depend on theta. Let me call it A or C. It's not. It could be that epsilon, could be anything else. Anything that doesn't depend on theta. So f of theta, I can expand that as A0 plus A1 theta. Now, if f of theta itself is a commuting object, we call it an even element of the Grossman algebra, then A0 would be an even element. But theta is an odd element, so A1 would be an odd element as well. But you can also consider f which is an odd element of the Grossman algebra. Then A0 would be an odd element, and A1 would be an even element. That even element itself could be a number like 7, or it could be the product of two Grossman elements again. It's just only an even element of the Grossman algebra. Now let me substitute this form, this is the most general form of f of theta into the integral, and see what we learn. Then we get here that the integral of f theta plus c, well, it is the integral of A0. Oh, and I will write d theta on the left. You will see that you do either one or the other. I find it always easy to do this. So I define my integral by writing this first. That's a notation. So then I get integral d theta. And now f theta, that is A0. Plus, and then I get the A1 theta plus c. And I want that this is the integral d theta of A0 plus A1 theta. Now I want my integral to be linear. That's an input. Now in Riemannian integral, I spoke of course linear, but here, if I require it to be linear, that's the simplest case, then you see that these terms A0 are the same on both sides of the equation. But A1 theta here, A1 theta is the same term too. So I conclude that the integral d theta of A1 times c must be 0. Now this should be true for any A1. So I can predict to take functions where A1 is the number 1. So then I see that the integral d theta of anything, if c is anything, but doesn't depend on theta, is 0. And that is, for instance, which I now write here again. So his first result is that integral d theta of something without, which is independent of theta, so something without theta is 0. Now, for completeness, you also have to specify what the integral d theta times theta is. And here you can put any number you like, but conventionally we write number 1 to make it as simple. You might say you can rescale theta by real numbers to make it 1, it's most important. So these two rules are now the integration of Berzin. And that explains what this symbol d theta means. So now we have this first thing.
A question?
Yes?
How can you set A1 to be 1?
Excuse me?
How can you set A1 to be 1?
Well, I didn't set one. I chose a function f. Every function should satisfy this rule. So in particular, I can take a function by a1 as 1.
But isn't A1 infinite?
Excuse me?
Isn't A1 an odd variable?
No, let me do it again. If I take f to be an odd function, then a0 is odd, but a1 can be even. And should go for all kinds of functions. Now, there was here a postdoc 10 years ago in the math department, and he wrote a little paper on boundary terms in the Theorem and integral. This is quite interesting, but I could never, can anybody tell me who it was? He sent me a note, and I often wanted to talk to him about it. He left Stony, and I have tried to trace him to ask people about it, but somebody remembers who he was. He wrote a little note. But anyhow, this is what most people do. This is called Berzin integral, but as I said, that postdoc knows, you can try to make different rules of this integral, but this is the rule I'm going to use. So then, I need something in terms of this field phi. Well, I claim that the good action which reproduces these two terms, these two, is written as a product of two phi's like this, and here enters a new object, what is called covariant derivative. And so now, I also have to get the transformation rules, which I have here, this one and this one. And I would like to write it in terms of one field phi. So phi is a function of x and theta. I would like to write a rule now. Now I'm going to introduce an operator q, which when it acts on phi gives the right answer. So let me write first the answer for q. I have dd theta plus I theta ddt. So this is an operator which can act on a function phi of t and theta. For example, I can act with dd theta on this function. Now I have to explain to you how dd theta acts on theta. You probably anticipate it, but let me explain that because there are usually a few details which are not always said. So I will define that dd theta acting on theta. And I like to write this now as an anticommutator for a reason which will become clear, is equal to 1. So what I mean by this, let me explain that next, and let me write it out. So dd theta acting on theta plus theta dd theta, because that's what the anticommutator means. Now this dd theta is an operator with x to the right. It can either hit this theta, and then you get 1, or it can move past it. But if this is antimoving, this is antimoving, then interchanging them gives a minus sign. It just cancels this. So this expression you can also write as dd theta acting on theta, and then I put this in brackets. This writing in brackets means that this dd theta can only act here, but it cannot move past. Now, there's an enormous confusion when people write these things, conjugate of this expression, let me formally do it. Now, in the Hermitian conjugate, I, by definition, interchange the order of two things. So the Hermitian conjugate, d theta, Hermitian conjugate, well, that becomes then theta Hermitian conjugate, d theta Hermitian conjugate. But theta Hermitian conjugate was theta. That's also this, d theta Hermitian conjugate. Now, this is a anticonjugate is symmetric, as you can see here. I can also put this in front and I get the same thing. So I can rewrite it as d theta Hermitian conjugate theta. And now, by comparing this with this, you see that d theta Hermitian conjugate is equal to d theta. So the derivative d theta is Hermitian. Now, I'm now at the level of calculus for Grossman variables. So I have to really do a lot of steps you do in mathematics, which usually as an undergraduate you get, but now I'm at the level of graduate students doing for any reason variable. Let me compare with the t derivative. If you write d dt, t, then I write a commutator. If I write it out, this would be d dt times t minus t d dt. And then if this t derivative goes past the t, I don't pick up the minus sign because this is now a commuting object. That's the rule on how you move one after the math vector pass beyond. But if the dt hits the t, you get 1. So this is 1 of the, let me write it here, 1. But if I now take the Hermitian conjugate of this equation, then I get t Hermitian conjugate, d dt Hermitian conjugate. And the Hermitian conjugate of 1 is 1. It's a number, a real number. Right? But the Hermitian conjugate of the real term of t is t. So this is t, d dt, Hermitian conjugate. But if I now interchange these two terms, I get the minus sign because the commutator means t, d dt dagger minus d dt dagger t. So if I reorder it, it's minus d dt dagger acting on t. And this should be 1 again. If I now compare the starting point with the end point, you see that d dt is an anti-Hermitian operator. So d dt Hermitian conjugate is minus d dt. So if I now look at this operator q and claim it as a Hermitian operator, because d theta was Hermitian, I can show that. d dt is anti-Hermitian, but there's an extra I. I will assume that theta and d dt commute. One is commuting, the other is anti-Hermitian object, so in principle I should be fine about this, but I can find it commuting. Yes?
And clarification, you sort of showed that two things have the same bracket with t, and therefore you said they're equal. Why is that true?
That's a good question. What else could it be? You say d dt dagger could be proportional to t. Yes, you're right, but then the dimension would be wrong. You see, t has dimension minus 1 and d dt has dimension plus 1. So that notion of dimension which physicists use would rule out this thing you propose.
This is non-degenerate somehow.
Well, you could have more variables in the game, and then d dt dagger need not be equal to d dt. For example, if I had 2 time coordinates, or time space coordinates, then maybe d dt dagger could be d dt plus ddx or something like that. But I have only 1 t and 1 theta in dimensions. So in my case, it's all unique. If you would have coordinates which are complex, then of course, in complex geometry, in the coordinate z, x plus y, and then ddz dagger is, the Hermitian version ddz is then ddz dagger. So if you have more variables, you can do more things. But I think this is unavoidable. It's a kind of quotient theorem. I'm saying you have something commuted with t is 1, something else commuted with t is 1. And let me say, notation. It's very obvious once you understand it, but it has to be explained, so that's why it takes some time about it. And if it moves past here, then the term where the ddt is all past, which I wrote here, cancels this term, the second term. So in the end, the only thing that remains is when ddt hits the t, and that is one. That's this one. Now, there's another operator d here introduced, and I'm going to give you the mathematical interpretation in a moment. This is what these people wrote down. But there is a beautiful geometry behind it, which I will not read today. But I will give you the ingredients first. And the geometrical meaning will then come tomorrow. There's another operator which enters here. It differs with the sign. It has a very nice algebraic property, and often these algebraic properties, when they are very pretty, have a geometrical meaning. Physicists often use the word geometry for algebra and algebra for geometry, but they're of course different things. So at the level of algebra now, well, alright. So Q, let's work out what the anticommutator to Q is. So it's dv theta plus I theta ddt, and another one, dv theta plus I theta ddt. Now, it is distributive and linear, the bracket, so this ddt, it cannot act on anything here, nothing depends on t. So, but this dv theta, it can hit this theta, or it can, but it cannot animate that. So let me work it out what it is. It is dv theta acting on dv theta plus I theta ddt. But this theta can move all the way past. Then the second term, I theta ddt, this thing. And then in the bracket, it sits on the other side. So plus dv theta, I theta ddt, times dv theta. These two terms is if I take this dv theta with everything here and write it out. Now here we have dv theta times dv theta. And I claim that dv theta times dv theta is 0. So lemma. dv theta times dv theta is 0. You knew already that theta times theta is 0, so now I claim that dv theta times dv theta is 0. I leave this as an exercise, and tomorrow, quarter early, if you can't do it, I'll prove it. But this is an elementary. Is it obvious? Okay, then. So I'm not going to prove that then. So this is 0. Now I get the next term. Now this dv theta, it can hit this theta, or it can move.
But that means compose off of it.
Yeah, two, one after the other. It's very easy to prove. One proof, of course, is anything that puts down to the right of here is linear in theta. This is one way of proving it. The dv theta on the thing with linear theta, remove that theta. And you're left with something which has no thetas in it. And then dv theta on something which has no thetas in it is 0. But you also do it algebraically using such things. Many ways of doing it. Now, if this dv theta hits this, you get something, 1, that's I ddt. So one thing is I ddt. And then if the theta goes past, then you pick up a minus sign, because dv theta and theta are anything object. And we also have the rule that if you interchange the order to anything object, you have a minus sign. But here, the same expression enters with a plus sign. So, if this dv theta goes past this term, you get a minus. Here, the dv theta has gone past the term, and it has a plus, and these two terms cancel. So the net effect is only I ddt. Now, then there is still this term, with everything else, and then let you check that also gives I ddt. So the net effect is that, I have to come to an end now, that there's an element in calculus of these and Q with ddt commutes, and D with ddt commutes. So this is a set of commutation relations involving anti-commutators of operators which are playing a role, Q, D, and ddt. Now to tell you, and then I should stop, what I'm going to do tomorrow, I'm going to tell you that these operators Q and D are operators which can act on a group element by coming from the left or the right. And since multiplication by left or right of group elements, and I will define what group elements we are dealing with, is commutative. It doesn't matter if it's a group element, if you first multiply from the left with something, then there's something else on the right, or if you first multiply from the right and then from the left. That will be the reason why Q and D commute, anti-commute. The operator Q will be the Lie derivative, or the symmetries, in the sense of Cartan. When Cartan wrote his famous books on Le Père Mobile, he used these ideas. We have just taken the book of Cartan and applied Cartan's ideas of cosset manifolds. In fact, we have not a cosset manifold, it's even easier than a group manifold. And we will derive what we call the moving frames, and should see that the Lie derivative is Q. The operator D, which is multiplying from the other side of the group element, which commutes this Q, is something which enters also in the work of Cartan. He has two moving frames, one due to the left and one due to the right multiplication, and the joint action of the group interpolates between these two. What we will use these for is in the construction action. And having that established the meaning of these things, I will then see how these operators act on the coordinates themselves. Here they act on the fields, but they also act on the coordinates themselves. And then we will see that in fact these transformations of lambda and phi, which can be written in terms of this operator Q, if you then execute Q in the coordinates, you indeed will find, so that is a result, it is not put in, and you will find that it is this operation on theta. So then we have seen that the original model I started with on fields phi, t, lambda of t, can be rewritten in a big space with a new coordinate theta called superspace. And the Lie derivative is then in terms of this operator Q, but when the Q acts on coordinates, this is how theta is transformed, and I'll also work out for you how t transforms. And that means that we have now translation in the fermionic direction. So local supersymmetry, the symmetry between the two kinds of bosons in our real world, is nothing else than translational symmetry in the other direction. So now we have translational symmetry in the time direction, and Andy Newton told us that there is a conservation law, and Weil in 1928 found out that means that energy is conserved. And now we have a translational symmetry in the theta direction, and that means that the symmetry between fermions and bosons in the world is conserved, according to Andy Newton's arguments again. Now these are far-reaching implications, of course, for the real description of nature. And it all comes out deductively from things. So I could have postulated for you superspace, so to say, by rules and this and this and this, as mathematics consistent. Instead, as all my lectures, I started from the simple thing, and I said by rewriting it. The new thing I did is introduce the theta. There was no deduction to do that. It may be natural that everything is symmetric between commuting and anti-commuting. For every phi you have a lambda, for psi you have an h. Why not for x and theta? And that kind of low-class logic we can use to think of things. Now, I've come to the end. Tomorrow I will then discuss more about superspace, and I will also show how the DRS symmetry in this model works. It's absolutely beautiful, and there I will make a lot of anecdotes again about Heisenberg and power and Lucy.
You said that the conserved quantity corresponding to time translation is energy, but I didn't understand what the conserved quantity was corresponding to phase translation.
Yes. That's the supercharge